Let's move forward. We got a very big view of what we can look forward to define our next applications, right? But let's see that when we start implementing, how will we, what kind of challenges we'll see. So I'm glad to invite, or I would say announce that Brady Benware is our next keynote speaker. Brady is the Vice President and General Manager of the Silicon Lifecycle Solutions Group at Mentor, a Siemens business, which is part of the Siemens Digital Industries Software Accelerator portfolio. In this role, Brady is responsible for test and product line, which includes design for test, yield, functional safety, and the embedded analytics solutions from recently acquired Ultra SoC. Brady is a 20-plus year veteran of the industry, has co-authored over 80 papers, been awarded 20 patents, and holds a PhD in electrical engineering. Brady, welcome.
Thank you very much, Naveen, for the introduction. Let me see if I can get my screen sharing to work here. Give me just a minute. Excellent. I assume that is coming through okay?
Yes.
Excellent. Okay, well, thank you so much, and hello, everybody. Hello, ITC India. It's great to be with everybody today. If not just virtually, it's still wonderful to see that the test community is still coming together despite the global pandemic that we face. I'm coming to you from my home here in Oregon, which is on the west coast of the United States, and I'm just absolutely thrilled to be here speaking with you today. So my talk today is really the continuation of a discussion that we started back at ITC, the North American ITC here in late fall. And it's really around this idea that as we go forward, we are seeing an increasing number of challenges associated with not just the traditional idea of test, but really when we start to look at the broader life cycle that an IC goes through, there are really an increasing set of challenges there that are really challenging the paradigm of test, and we see that the role of test itself is expanding significantly here in recent years. And so for a little bit of context, it really is a situation, and what's really driving all of this is that we have entered a new context for ICs. We have an environment now with the applications that we're envisioning for the future, a situation where we have electronics that are extremely complex and deeply connected, really interconnected systems that are bringing forth these new applications. And so things in communication around 5G or data center, some of the things with IoT and the connectivity of all of this is really a new context for a lot of these ICs that are bringing these new challenges. But the good news is that if we can solve these challenges, this new context is really quite compelling from the standpoint that this is really going to bring about some very significant social benefit. And if you look at this study from McKinsey and Company talking about the benefits of a smart city, for example, you can see that it has really some pretty significant social benefit, from lives saved to reduction in crime or faster emergency response times. One of my favorite here, which is not very applicable today, I hope it becomes applicable again, is this 15 to 30 minutes shaved off of the daily commute is estimated by introducing smart cities. And I don't know if anybody is similar to my situation, but my commute is about 30 seconds as I travel from the kitchen to my spare room to conduct the day's business. But I do hope that at one point this benefit to society actually comes back for us. And so with those kinds of benefits, obviously there are going to be serious economics that follow along with that. And it's estimated that just the global smart city market alone is growing at a rate of around 20% a year, and is expected to reach about $190 billion in 2023. About $24 billion of that is expected to be the ICs that make up these complex systems. So obviously, with the benefits that we have, the potential benefits that are there, and the economics that are associated with it, it's going to drive the development of these technologies. It's going to drive a tremendous amount of innovation, and a lot of those developments are going to create new challenges for test. So as we look at what some of those challenges are, obviously we're going to be faced with a lot of challenges that we've seen in the past. They're following along in a similar vein of things that we've seen in the past in terms of things like process technologies. Obviously, as we get to 5 nanometers, the current state, and coming up here on 3 nanometers relatively quickly, every generation of process technology that we introduce brings about new test challenges. But these are really challenges of a variety that we have seen before, we have faced before, and we have really the culture and the industry available to deal with those challenges, and we'll solve those problems. But as we look at some of this new context and what's happening today, we're seeing that it's no longer just things like process technology that's driving that change and the additional challenges. For a long time, in recent history here, there's not been a whole lot of investment in new types of design architectures, but in recent years we've seen a flurry of activity in the investment space, significant amount of additional venture capital funding for new design architectures. And I don't think it's going to surprise anybody to see that at the top of this list is really what's going on in AI and machine learning, where, from the data that's here, it was about over a 3-quarter period, there was an investment of close to $1 billion in new kinds of architectures for AI and machine learning. And closely behind that, you see that the investments in communications. And so, at the end of the day, it's really about, these investments are really about either processing data or transferring that data around. And you can see that that's leading to this, this new future of interconnected systems. But that investment is creating a lot of interesting new architectures. And I think this is probably one of the most interesting developments that I've seen, which is the Cerebrus wafer scale engine processor for AI applications, where it's this enormous 1.2 trillion transistor computation device for AI applications. And that's obviously significantly larger than what we've traditionally thought of as large devices. So we are seeing new and exotic architectures, design architectures, that will also introduce some new test challenges. But really, it's not just the design architecture, it's not just the evolution of the process technology, it's also the evolution of the use cases. And I really enjoyed Ricardo's talk, talking about what's going on in the world of autonomous vehicles, and certainly, autonomous vehicles have become a bit the poster child of some of this evolution, and the interesting new use cases we have for ICs. But really, if we look across the broad spectrum here, whether it's about what's going on with cloud and data center and processing a lot of very personal data that we all have, or it's making medical devices smarter and making those connected so that doctors can better serve patients in a remote fashion. It's clear that as we go forward that more and more of the human experience and the well-being of our societies really depends on the safe, secure, reliable operation of the devices that we're using to deploy these applications. So we are getting to a situation where electronics and the ICs, and when we have problems, these are situations where we can no longer look at these as an inconvenience. But really, when things go wrong with these devices, they have catastrophic effects, and it's really quite unacceptable to let these kinds of of problems happen, as was the case with this very tragic accident in China in 2011, where an electrical lightning strike took out the electrical aspects of this commuter train and resulted in this accident. And so it's this situation where our human experience and our well-being, being so dependent on these ICs, is really driving the need to ensure that they are functionally safe. And Ricardo just had a great talk about a lot of the things that are going on in the world of functional safety, especially for automotive. But what's interesting here is that, you know, it is other safety critical industries as well. And so you see some of the standards related to functional safety, where it's really about making an assessment of what could possibly go wrong and then making sure you have a way to mitigate those issues. And, you know, I think that the trend that we see here from surveys like the Wilson Research Group survey that surveys verification engineers every couple of years, we're hoping to get the latest data here pretty soon. But we see that survey over survey, we see an increase in the number of respondents who say that they're working on projects that are related, that have functional safety requirements. And so we are seeing this increase in the need for things like functional safety across a broad number of industries. And as we look outside of safety critical industries, you still have some of the same concepts at play in terms of needing to be able to detect when something goes wrong and being able to mitigate those issues. And in things like data center applications, that's called resilience instead of functional safety. Obviously has very different characteristics, but the basic idea of needing to monitor these devices over time remains the same. You also heard Ricardo talk a little bit about security and what's going on in that realm. And certainly this is an area where, you know, it's not just about what can go wrong from an unintentional situation. It's really about what can go wrong when it's a malicious kind of situation. And so the graph you see here on the left, this exponentially increasing set of data points, are the number of new entries in the common vulnerabilities and exposures database. Really, these are just the vulnerabilities that are discovered year after year. And these are not cumulative. These are really exponentially increasing year after year in terms of the new discoveries. And we're seeing that these vulnerabilities are discovered across a broad array of markets, from the medical market, automotive. I think folks have seen before the Jeep that's the demo of the Jeep that gets taken over by hackers that come in through the cell network and then are able to reverse engineer the CAN bus and issue commands over the CAN bus and really take control of driving critical systems and have serious effects. But we're also seeing it in the consumer space. This Nest camera, for example, where hackers infiltrated the camera, and while not a safety critical issue, certainly it was very scary for this family whose Nest all of a sudden had the voice of somebody warning them of an incoming missile attack. And so we see these vulnerabilities and these security issues across a broad array of markets. And having a significant impact and things that need to be addressed. One of the really interesting things, though, as we look at what are the impacts associated with some of these vulnerabilities, it's interesting to look at some of the business model that some researchers have now started to use to get paid for the research that they're doing in the security area. And so this is actually an example of a St. Jude's medical device implant. It's a pacemaker. It's a medical Internet of Things connected smart device. And these researchers, these security researchers, are able to discover a vulnerability that could lead to the possibility of a shock instead of really administering the proper sequence for the pacemaker. And rather than simply publishing these results in order to really monetize their effort and the work that they put into this, they partnered up with a financial firm that specialized in short selling. And so they coordinated with this firm to take up a short sale position within the company before announcing and ultimately publishing the vulnerability results. And this led to certainly a very large drop in the valuation of the company. In this case, it was about $1.5 billion drop in valuation, and a nice healthy profit for these security researchers. So it's going to be important that with these vulnerabilities that exist in systems, that these systems also have ways of monitoring what's going on and having proper mitigation techniques so that when those are discovered, they don't result in these kinds of financial issues for companies. So when we take a step back and kind of look at this broad array of challenges from the new process technologies or some of the other things that are going on in terms of modular design, the more than more, the 3D packaging, 3D ICs, or these new architectures, we see that we have really two classes of challenge. These that are the variety of a greater complexity, and things that we have to some extent seen those kinds of activities before. And then we also see these challenges associated with higher levels of quality or security, reliability, functional safety, and resilience, which are really looking at this set of requirements that really extend further into the life cycle. And so as we look at these two challenges, we really see that there are kind of two vectors of innovation that are going to be required going forward. The first variety of this greater complexity, but of a nature that we've seen before, is going to require more innovation within some of the traditional realms of things like design for test. But as we get into these increasing lifecycle requirements, we're going to be needing things that are more along the lines of design for more than test. And so these are the two things I kind of want to explore a little bit further here for the remainder of the talk. And so in the first case, really, while there are a lot of challenges associated with those additional complexities, and we could spend a lot of time talking about a lot of the innovations that are going on and are needed to address those, there's one in particular that I think is worth talking about, and it has a lot to do with bandwidth, test bandwidth, and how we're leveraging that bandwidth to do the testing that we do today. And so as we look at things like modular designs, and as we've gone from ASICs to SoCs and getting into the area of 3D ICs, we see this increasing amount of modularity. And we know that our techniques for instrumenting the design with design for test technology, scan test, and other forms of test, we need to have a flow that mimics that modular design approach, so that we can do DFT at the modular level, at the block level, the core level, do our pattern generation, do our verification, all at the core level, and then be able to kind of plug and play that all the way back up to the chip level for the integration. And today there are many techniques for doing this, and great solutions like hierarchical DFT that help us achieve that. But when we look at the increasing level of modularity, there's an increasing challenge that's coming, which is that basically today, as you do that design flow and as you do the DFT implementation, you're having to establish up front some choices around how much bandwidth of the scan test data channels that you have access to, how much bandwidth you're going to allocate to each one of the cores. And you make these decisions up front, and as you get through the process of generating test data and implementing the DFT, you find that those choices that you made up front were not necessarily optimized. And so you're left with a situation where you can either iterate on that and achieve a better test time, reduce the waste of bandwidth, or do that linear bottom-up flow and deal with the increased associated test cost. And so this is one of the key challenges, especially as we get larger and larger designs that are more and more modular, that need to be solved. And really, we're just at the precipice here of entering a new era within scan test in particular, that what we really need to bring to solve this problem are innovations around the idea of more of a programmable bandwidth. And so when you look at a technology like the streaming scan network that we've been working on, it's really a situation where you can define the architecture up front in a static manner, and then that bandwidth gets configured later on in the design flow with a few bits from the scan test data itself in order to configure that and really tune that exactly to the kind of bandwidth that's required. And when you do that, you have this opportunity to continue to have a linear design flow without those iterations, and at the same time ensure that you're getting the optimal usage of bandwidth and distributing that bandwidth appropriately. But similar to this, and along the same lines of bandwidth and the challenges that we face here, certainly one of the trends that we've been seeing for a long time is that gate counts inside of the designs continue to increase exponentially. Pin counts increase at best linearly over time. And so what we're seeing in terms of how this is being dealt with from a primary design purpose or functional purpose of the design is the introduction of high-speed IOs. And we're now in a certain situation where in many cases high-speed IOs are dominating the IOs in the design, as was the case in this eSilicon presentation from ITC North America a couple of years ago for this AI platform where about 200 out of the 236 IOs were SerDes based. And so as we go forward, it's not just a matter of being able to distribute all of that data to the cores appropriately, but we're going to have to leverage those high-speed IOs in order to get the data in and out of the chip. And so when you look at a standard like 1149.10, this is a great way to achieve this when you combine that with this distribution network to distribute that data effectively. The 1149.10 standard allows you to continue to have a dedicated test protocol, leverage that high-speed I/O, but ensure that you're really testing all of the same capabilities that you have the ability to test in a traditional GPIO kind of fashion. So when we look at these challenges, again, there are many more aspects of this category of more design for test, but that's one of the really key ones that we see going forward that's going to set us up for another decade of scaling for scan test. The other area here is in this increasing lifecycle requirements and the need for this design for more than test. And here we've already seen how test and the role of test has expanded into this area. When you look at functional safety and what's required within automotive, a lot of the things that Ricardo was talking about, what's really happening is that test is inside the design. It's really this comprehensive safety subsystem where test is integrated as part of that. And so when you look at what's required here for a comprehensive safety subsystem, it really is about having those low-level safety mechanisms. It's about having a control network to interact with those safety mechanisms. And then at the top layer, you need the hardware and safety manager in order to be able to initiate these tests, detect any issues that are occurring, and be able to move into those safe modes of operation that Ricardo was talking about. And so you can see that already, these worlds of kind of the world of test and the world of this lifecycle management are already converging within these subsystems that are integrated into designs that require these functional safety requirements. And of course, we need to continue to innovate in this area. One of the real challenges as we go through the different levels of autonomous drive, and especially as we get into those higher levels of level 4 and level 5, eliminating that driver fallback, the fault-tolerant time interval that's required, that time to detect and have that reaction and move into that safe state continues to shrink. We find that the requirements continue to evolve, and we're needing to do that diagnostic test faster and faster. And so when we look at some of the innovations that are required here and some of the innovations that we are making in this area, there really is, just looking at one of these examples on Logic-Bist, you can see that there's a capability an innovation here that is really about moving from the idea of the traditional logic bits, which is a per pattern observation where we're really observing for faults basically once every time you do a sequence of loading the scan chains, doing a capture and unloading those scan chains, to this observation scan technology, which is really a per cycle observation for a large part of the circuitry. And so the idea here is that by adding a specialized scan chain that can observe every cycle instead of just doing a capture once per pattern, we can observe these specific locations within the design, and that increased observability by being able to do that every cycle, we can have a significant reduction in the number of test patterns that are required to achieve those coverage levels that are needed for those functional safety requirements. And so this addresses that functional or that faster detection requirement. But the other side effect here is that it reduces the aging. If you can reduce the total number of test cycles that are required to do that diagnostic test, you can have a significant reduction in the amount of aging that's incurred as a result of the monitoring that's being done during the operation of that device for its primary purpose. Now, as we look at some of these needs and some of these capabilities and some of the challenges that we have, when we look at what's been going on in the world of test, there's a very large focus historically and currently on really what I would call structural monitoring. And so as we look at things like what can go wrong in the system, we're talking about things like defects or degradations or these random faults, alpha particles that can cause disruptions within the state of the design. And a lot of what we have for those functional safety requirements are really focused on this structural monitoring aspect. But when we look at the comprehensive system, there are other things that can go wrong. And Ricardo talked about some of these as well. But certainly you can have situations where there are hardware bugs or software bugs, despite our best efforts to eliminate all bugs, especially in the software layer. We see it's very difficult to create bug-free software. And so when that gets out into the system and it gets exposed to a surprise use case, that can create unintended failures that are not observable through these structural monitoring technologies. You can also have situations where you have the malicious attacks, these security threats, these vulnerabilities, where again, everything structurally in the design is continuing to work perfectly fine, but there is this increased level of activity that you really have to have some amount of monitoring of the functional activity in order to detect. And so really to have a comprehensive set of solutions, you need both the structural monitoring as well as the functional monitoring. And today these are very different worlds. And we believe very strongly that these two worlds need to come together in order to really drive that next level of innovation that's going to address some of those future requirements for the complete life cycle. And some folks may have seen the news that we believe so strongly in this that we recently acquired Ultrasoc, and we're integrating that as part of the test products at Minter. And Ultrasoc is a company that's focused on that functional monitoring with their embedded analytics in order to address some of these challenges of debug, safety, security, and optimization. So I thought it would be useful to have just a brief look at some of the innovations that have occurred in this functional monitoring area to give you a sense of a little bit about what is there and why this makes sense to really think about this in the context of test, where traditionally it hasn't been thought of that way. And so when you look at a kind of a typical SoC, all of these little green bubbles on the slide here are really, the main components of a typical SoC. You'll have some processor cores, a DRAM controller, some custom logic, some other interface controllers, and a NOC that's connecting all of this together. And these little blue bubbles here in the first layer below the green processor blocks, these are really various monitors that can observe what's going on with those processor cores in those analytic modules, where it can collect data and gain the insight into what's happening functionally within the design. You then have a messaging fabric which brings that data out and finally interface that either to debug environments, manufacturing test environments, or embedded systems. And when you look at something like this and you compare that kind of to the picture that I showed before about embedded systems, these subsystems for functional safety, you realize that really, whether you're doing the structural monitoring or the functional monitoring, these are really separate subsystems today. But these subsystems do have the ability to detect things like safety-related issues. It can monitor the bus traffic and identify that there might be a stuck pixel, or in a security application, being able to detect abnormal latency with respect to the CPU processing, or in an optimization application where it's looking at cache misses to better understand various workloads and what the effect of those are within the hardware. And so this idea of having non-intrusive hardware-based monitoring technologies and instrumentation really give you that very fast ability to detect issues and really apply those for these other life cycle considerations. So kind of taking a step back from everything I've talked about, the key concept here that I really want to convey is that I do believe that we're headed into a realm where we're moving from a traditional view of test and this idea of design for test into a realm more akin to something like design for lifecycle management, where today a design is designed for its primary function, and those designs need to be augmented, instrumented, in order to really meet the challenges of the remainder of the life cycle. So whether that's in that realize phase, the manufacturing phase of needing to do debug, test, and yield, or out in the end-use phase in the utilize arena, adding that safety and security or optimization capabilities. And a lot of this is, when we break that down into kind of that structural monitoring versus functional monitoring, these two worlds really need to come together in order to effectively address all of those capabilities. Now, the other aspect of this is that it's not just about pass-fail. You look at a lot of these needs in that life cycle, and it's really about collecting data and being able to leverage that data both for feedback, continuous improvement through earlier phases in the life cycle, or taking data from earlier in the life cycle and leveraging that in a feed-forward mechanism to do things like predictive preventative maintenance and those kinds of capabilities. So as we go forward here, we really believe that this community, this test community, is the right community to tackle not just the traditional role that test has had, but really tackle these additional life cycle challenges and be able to innovate within this expanded role. But to do that, we really have to move past some of those traditional paradigms of we do need to continue to do pass-fail tests, but it's about also doing collection of insightful data. We do need to continue to test for those structural aspects, but we also need to do testing for those functional risks. And it's not just about standalone. Certainly doing standalone tests of an individual device, understanding why an individual device might be failing, getting protection for safety and security on an individual device by itself, we have to also look at these things from a statistical nature. Really, truly solving some of the safety and security challenges will require that we're collecting data from not just one device and understanding how that affects that one device, but a whole fleet of devices that are deployed in a particular application, understanding, receiving the data from all of that, and identifying anomalies in there. Because it's one thing to be able to know all of the policies ahead of time for what could go wrong from a safety and security standpoint, but it's another thing to be able to leverage the fact that a device is misbehaving in an unknown way, that we can add additional protection and additional detection of when things go wrong. So with that, I'd like to close just by saying I think this is a very exciting time, not only for the applications that are coming our way and the technologies that you all are working on are helping to create, but this really is an exciting time, I believe, for test. I've been in the industry for about 20 years now, and throughout that time I've been interacting with test in some form or fashion. And it feels very exciting at this point in time to see how test is actually becoming a part of even more aspects. It's being challenged to address some of that. And I really look forward to the innovations that this community is going to come up with in addressing those challenges. And I look forward to that. I thank you for your time and look forward to your questions.
Thank you, Brady. That was very good talk. Quite a lot of topics covered. At this time, Kavita, do we have any questions from the audience?
Yes, we do have. Brady, the first one, what are the new DFT architectures and solutions that need to be introduced to achieve low DPPM numbers? Will adding these new architectures also affect the numbers since they also might have defects?
Yeah, so great question. In terms of quality, certainly there are couple of aspects there. One is being able to make sure that you can continue to generate highly effective, highly efficient tests, and some of the architecture that I talked about in terms of this things like streaming scan network, being able to distribute that bandwidth effectively is going to be an important part of that. Now, in addition to that, we are certainly seeing that there are, a continual evolution of fault models, that over time we have seen the addition of fault models again and again, and we've moved from very abstract notions of what faults are to very defect accurate versions of models that are increasing not only our ability to provide higher levels of quality, better DPPM, but also better understand those defects for yield learning purposes. And so we do continue to see that evolution and continuing need to drive to increasingly accurate versions of defect models in order to achieve those quality levels in the future.
So next question is there a possible correlation between advanced fault models with the lifecycle challenges, or does it require more stress test and system level test?
Absolutely. We are, I think it's interesting to watch the industry evolve in the area of things like functional safety and the traditional definitions and what are in the standards for what you have to be concerned with. And we think we're getting into an era where what's defined in the standards is not 100% sufficient, and the interpretations there are somewhat different depending on what company you might be talking to. But we certainly see the need that a lot of these advanced fault models that are being used in manufacturing tests need to transcend their way into those in-system tests, and we are seeing the need for higher levels of coverage than really what are dictated by the standards. And the companies that we talk to, some are viewing that as a potential competitive differentiation. That going beyond what's really required by the standard, providing those higher levels of coverage, is really a way that folks can outdo one another, and we're starting to see signs that people are interested in doing that.
Do we have time for one more question, Amit?
Yes, let's take the last question.
Okay. So here's the last question, Brady. Should we consider developing hardware security standards for commercial as these devices enter personal space and hold sensitive personal data? Today, commercial chips devices are low on reliability, functional safety, and cybersecurity. Hacking into a home air conditioning and lock the house through home security is a risk.
Yeah. From my perspective, yes, we should, and I believe that we will. as I alluded to, I think we are moving into a world where more and more of our livelihood depends on the safe, secure, resilient operation of the devices that we depend on. It's interesting that anytime I travel now, I absolutely take it for granted that my phone is just going to work. I'm going to be able to get directions anywhere I need to go. And if I'm in a car trip in the middle of the desert, I can rely on my phone to make a call and to somebody to help me if I get into trouble. And these are things that we're now taking for granted, and really our livelihoods do depend very heavily on the electronics that we have. And so your examples of electronic door locks and things of that nature, they not only need to be resilient and ensure that we can continue to use them, but certainly we need to introduce more security into these systems and ensure that we can detect those intrusions and do something about them when we do detect them.
I think we have one more upvoted question. Can you please elaborate on the programmable bandwidth for EDT?
The programmable bandwidth for EDT, is that
EDT.
the question?
Yes, that's right.
Yeah. So I think you can look forward to hearing more about that in the future. But the basic idea there is that these are configurable blocks that have very standard. It's like a bus in a design that has a standard number of channels to it, and that interconnects with the scan delivery system for a individual core, and there's some configurable logic in there that does a matching between those two bandwidths to ensure that you can really leverage the amount of bandwidth and peel off just as much bandwidth off of that bus as you need to service that core, and let the rest of that bandwidth get used for other cores. And so by doing that and having that configurability, again, it has the ability to define that architecture up front, but really configure it downstream once you understand how much bandwidth is really needed for each of those cores. That is configured as part of that, can be configured as part of that data stream to ensure that you're getting the right bandwidth to the right cores.
I think that's all we had, Ravi.
Thank you, Kavita. Thanks very much, Brady. That was a very good talk to walk us through some of the upcoming challenges, as well as connecting it to the whole lifecycle management, rather than just design for test, but more than test. On behalf of the whole team, ITC team, I would like to thank you for your time. I know it's late night for you, but taking time out for preparing and then presenting to all of us. Thank you so much.
Yeah, my absolute pleasure. Thank you very much for the opportunity. It's great to speak with you.
Absolutely.